As discussed in the introduction on vector concepts, speed is considered a scalar because it's just a magnitude. If I'm traveling 100 kilometers per hour but I give no indication of direction, that's just a size or an amount, so it would be a scalar. But now if I say I'm driving 100 kilometers per hour south, it becomes a vector because I have both magnitude, 100, and direction, south. So velocity always implicates that you have a magnitude and a direction. So we're going to use vectors to represent velocity because that's what vectors are. They have magnitudes and direction. So a swimmer swims straight across a river at 1 kilometer an hour. So I have a river, and the swimmer heads straight out, and they're swimming at 1 kilometer per hour. The river is 45 meters wide, so I'm going to kind of hold on to that's the distance across the river. And the current runs down the river at 2 kilometers per hour. Well, down the river just means somewhere in the middle of the river, and it doesn't matter which way you draw it. I'm going to draw it this way, but instead of drawing it in the middle, I'm actually going to draw the current there because the whole current is moving this way. The reason I do that is now I have it tip to tail. So this one is 2 kilometers per hour. So even though the swimmer jumps in and is swimming straight across the river, the current is actually going to make them travel this way. They're going to be pushed here. So when it says how fast is he crossing the river, we're actually looking for this speed here because this is the actual speed that he's crossing the river with. Well, the good news is I have a right angle triangle, and these are all velocities, so it has to work. So this velocity or this speed, the magnitude of it is going to be this root of 2 squared plus 1 squared. That's just Pythagorean Pythagorean theorem. I square 1, square 2, add them, and then root it. So it's going to be root 5 kilometers per hour. How far downstream will he end up? So now we're looking for a distance. Here's where I have to be careful with my triangles. 2 kilometers an hour is not a distance. I have 45 meters here, and I know there's going to be some distance there, that by the time he makes it across this 45 meters traveling this way, he's going to end up pushed down river a little bit. But before I do that, I realized it asked for the swimmer, how fast. Okay, I did answer. If it just asked for the actual velocity of the swimmer, I would have had to find that angle direction. But because it just says how fast is he crossing the river, root 5 kilometers is enough. But now I have this triangle. The information in these triangles can't mix. I can't mix speeds with distances. However, these triangles represent the same situation, so they are similar triangles. So I can set up a ratio. D from the distance formula matches up with 2 from our speed or velocity triangle. And that's the same as 45 meters matched up with 1 on our velocity triangle. So by cross multiplying, I get 90 meters. So he's traveling, so he is crossing at root 5 kilometers per hour and will end up 90 meters downstream. 2. Similar type question, but now we're talking about boats. A boat crosses a river at 10 kilometers per hour. The current flows at 3 kilometers per hour. How long is it going to take the boat to cross the river if it's 500 meters wide? And what direction should the boat travel in order to end up straight across the river from where it launched? So I have my river, and in this case, it's 500 meters wide. The boat is going to head out, but the boat isn't heading straight across and getting pushed downstream. It's asking us what direction should it head so that it gets pushed downstream. So the boat is actually heading that way deliberately and traveling at 10 kilometers per hour. So the speed of the object always goes on their intended path. In our first example, the swimmer was trying to head straight across and ended up getting pushed. So we put our 1 kilometer there. Here, the boat is trying to head up here, but then the current is going to push them where they actually want to end up, which is here. So I have my 10 kilometers hour, and it say how long will it take the boat to cross the river if it's 500 meters wide. Well, the problem is this 500 is straight across. The boat is actually going to end up traveling a little bit more than 500 meters. But I can figure out, this is 3. I was missing a piece of information there. I can figure out what this is using Pythagorean theorem. So the actual velocity crossing the river straight across is going to be the root of 100, or 10 squared minus 3 squared. So it's going to be root 91. Because 10 is the hypotenuse, so I square 10, square 3, subtract them, then root it. So now hopefully you think back to our speed, distance, and time formula. That distance is speed times time. Even though we've made the differentiation now that we're dealing with velocity, this still holds true. So if I want to figure out the time it takes to do something, it's distance divided by speed. Here's where I have to be careful though. This speed is in kilometers per hour because it's the same unit as what was given to me. This measurement is in meters, but 500 meters is actually 0.5 of a kilometer. So my time is going to be 0.5 divided by the root of 91. And I'm going to actually do that in my calculator to get an idea of time. So 0.5 divided by the root of 91. And it is 0.05 of an hour. I'm going to change that to minutes by multiplying by 60. So it's actually going to take like 3.1 minutes, or just over 3 minutes for the boat to cross the river. Now, what direction should the boat head or travel in order to end up straight across the river? Well, that's going to be this angle here, because that's going to tell me how many degrees to turn and head upstream in order to compensate for the current and have it push me straight. I'm going to just use SOHCAHTOA. And because now I have all 3 sides, I can really use sine, cos, or tan. I'm going to stick with sine though, because the 3 and the 10 were given to me. So even if I made a mistake in this calculation, I could still get the same or the right answer for the angle. So I'm going to say the sine of theta is 3 over 10. So theta is going to be the inverse sine of 3 divided by 10, or 0.3, which is 17.5 degrees. So therefore, it will take just over 3 minutes, and the boat should head 17.5 degrees upstream. Another type of situation that involves velocity is airplanes. So we have an airplane heading southeast at 650 kilometers per hour, and it encounters a wind of 80 kilometers an hour from 36 degrees south of west. What is the ground velocity of the plane, and in what direction is the plane actually traveling? Because the plane's actual path of travel is the resultant. What is the plane trying to do, and what is the wind causing it to do? The resultant is always the addition of 2 vectors. I'm going to give myself a compass and make it quite big. Actually, I didn't need so much on the top part, so I'm going to focus down here. So an airplane is heading southeast. Southeast is right in the middle. And 650 kilometers an hour is fairly fast, so I made it a fairly long vector to represent that this velocity has a bigger magnitude, especially when I compare it to the wind, which is 80 kilometers an hour. So now it's encountering winds. I'm going to first put the winds up here, and then I'm going to transfer them down there. So 36 degrees south of west means you start at west and you move 36 degrees south. So that's the line that my wind's on. But it's coming from that direction. It's not heading in that direction, it's coming from that direction. So that's what it looks like there. And 80 kilometers an hour, although it's pretty strong winds compared to our 650 for our velocity of an airplane, it's quite small. So I represent that. So now I'm going to move that there. And then the actual path of the plane is going to be this resultant. And ground velocity is, if I look from the ground to the plane, I actually see it moving. I can't separate the wind from the plane's actual velocity. So the ground velocity is the resultant. I only see how it's traveling given all the forces acting on it. So ground velocity really is just always what's the result of the wind and the actual direction of the plane. So now I have two lengths on this triangle. However, I cannot assume that it's a right triangle because the wind and the plane aren't perpendicular to each other. But I have lots of information up here. If this is 36 degrees, this is 54 degrees because they have to make 90. This is 45 degrees there because southeast is right in the middle. So these two together are 99 degrees, 54 plus 45. I have a Z pattern or alternate angles because the wind is parallel to itself no matter where it is. So I come along here, go down and go there. That means that is a 99-degree angle as well. So now I can find the magnitude of the resultant using cosine law. So the magnitude of the resultant squared is going to be 80 squared plus 650 squared minus 2 times 80 times 650 times the cos of 99. That's just cosine law. I'm going to type it into my calculator, and I'm going to square root it to go right to the actual magnitude. And it's 667 kilometers per hour. So the wind is actually working with the plane to speed it up in this direction. But the ground velocity of the plane, I have the magnitude. Now it's asking in what direction is the plane actually traveling. So now I want to come up with a way of representing the direction of the plane similar to how it was given to me. I want to use the compass direction. But in order to do that, I need that angle up there. Now that I know that that is 667, I can use sine law to find that angle. So sine of theta over 80 equals sine of 99 over 667. So theta is going to equal 80 times sine 99 divided by 667. Second sine, 6.8 degrees. Or I'm going to round up to 7 degrees. So that means in here is 7 degrees. But if I just quote my direction as 7 degrees, that's not going to match. However, if that's 45 and that's 7, I have a total of 52 degrees there. That means this here is 38 degrees because the last time this was given as 36 degrees south of west. So then we're actually heading 38 degrees south of east. So therefore the plane is traveling 38 degrees, south of east at 667 kilometers per hour.